All right, so here is our example. This is our circuit right here. We see that there's a switch, so this is a first order circuit. Two resistors, there's a resistor and there's a resistor, don't confuse it with an inductor, voltage source, and a capacitor of 25 millifarads, okay? The voltage on the capacitor is oriented as such, plus minus, top to bottom, and then the current passes downward through the capacitor. Now that doesn't have to necessarily be that way, it's just the way that I've designed it. So we're going to solve it with these assumptions. We want to find the voltage on the capacitor as a function of time, graph that function, and then find the current through the capacitor at 0 minus, the instant just before the switch pops, 0 plus, the instant just after the switch pops, and then at infinity, basically a long time after the switch has already popped. Okay, so like always, we just draw our 4 boxes. And we'll start, actually, you know what I'll do? I'll bring it over to the side a little bit. We'll draw 4 boxes and we'll just go. Don't think about it too hard. Only think about each circuit in itself, but drawing the boxes and what they represent, don't think about that. That's already kind of been laid out for us. So we got our 4 boxes, each representing the 4 or the 3 times and then the tau. All right. So first we're going to do our zero minus analysis, because remember the voltage on the capacitor does not change instantly. So V0 minus is V0 plus ultimately. So draw the circuit before the switch happened. The switch was open. So what you're going to have is this, a stable capacitor, all right, and a resistor. But the thing is, that's stable, and that's a 0 minus. There's no power coming to this circuit. It's not like there's current coming inside. It's not like there's a voltage being applied anywhere. So that means the voltage right here, even though it's stable, has to be 0, has to be stable at 0. So VC, 0 minus, is VC at 0 plus, and that is 0. Okay. So that was pretty simple. Second one, the switch is going to be closed now. So you draw the circuit with the switch closed. Okay. Put the 5, draw the switch closed. Now plus minus is where the voltage on the capacitor is. So that's the voltage on the capacitor at infinity. And it continues and as such. Now mind you, this happens because the capacitor is stabilize, and when it's stabilized, it's acting like an open. So that's what we put there. This is basically our circuit. Well, if you say this is A and this is B, this 20 is also sitting between A and B. Therefore, yeah, the capacitor is sitting right here, but it shares the same voltage with this 20 ohm resistor because they're both between A and B. Okay. So with that being said, all I have, if I were to just kind of draw this over here, basically I'm looking at a voltage divider circuit, and I can simply say the voltage on the capacitor at infinity is the voltage divider, which is to say 10 times by the resistor that I care about, 20, over 20 plus 5. Ooh, that's ugly. 20 plus 5. 25. And that number is 8. So I'm going to, wait, hold on, 10 times 22, yeah, 200 over 25 is 8 volts, okay? So it starts at 0, goes to 8, so we know this thing is going to be charging, all right? Now I just got to find out how fast it's charging, and that's all based on my tau circuit. And my tau circuit is always based on my after the switch configuration, so I'll be using this circuit. Please remember, the 0 minus configuration is the only time you use the before switch configuration. So I'll come up here, I short my voltage, and I short it because I'm turning it off. Turn off a voltage source, it turns into a short, all right? And I label where the capacitor and or inductor is, AB, all right, because that's what we're trying to find the resistance around. This is my 20, this is my 5. If you're paying attention, this 20 and this 5 are not in series between A and B. I got to go between A and B. Between A and B is the 20, between A and B is the 5. So 20 and 5 are in parallel, okay? Parallel. So my REQ is going to be 20 in parallel with 5. 20 times 5 over 20 plus 5 is 100 over 5, which is 4. Okay, that means that my tau is going to be, since this is a capacitor, 4 times by the capacitance value of 25 milli is 10 to the negative 3. That is, oh geez, what is that? 0.1. 0.1, and then it'll be 0.1 seconds. Great. Okay, so with that being said, I have everything I need to actually go get myself this voltage function. So I guess I'll do it in green. Put a little arrow right here. Okay, remember it's always final plus initial minus final, e to the negative t over tau. So plugging that in, the voltage on the capacitor as a function of time is going to be the final value, which is 8, plus the initial was 0 minus the final is a minus 8. So it's plus a negative 8. So I'll just put 8 minus 8. E to the negative. Now t over tau is 0.1. 1 over 0.1 is 10. So instead of writing t over 0.1, I'm just going to do 10t. This right here is my first answer, the voltage function. All right. To graph it, it's going to start at 0. Voltage in this will be seconds. It's going to start at 0 and go to 8. So I'll just go up like that. But please do not forget, this has to stabilize. It stabilizes at a very specific point. It stabilizes always at 5 tau. 5 tau, in this case, is 5 times 0.1, or 0.5 seconds. Okay, so it goes to 8 after 0.5 seconds. Bam, the second part, the graph has been done. Okay, all that's left is for me to find the currents through the capacitor at these different times. All right, so let me just go back to my analysis points. Since this whole circuit is devoid of any energy, if there's 0 voltage and there's 0 energy, there has to be, that's not an L, that's a C. It has to be 0. IC 0 minus equals 0. Okay, come over here at IC infinity. IC infinity, okay, that's basically saying, let me put it in red, the current right there. Okay, the current through the capacitor. The capacitor is behaving like a short, but it's behaving like an open right now. An open, by definition, means that there is no current. That's the whole definition of it. So IC, not at 0 plus, but IC at infinity is equal to 0. The 0 plus situation is always used to find the opposite value of the function at 0 plus. So what that means is you'll always find I of the capacitor at 0 plus with the 0 plus box. You'll always find V of the inductor 0 plus at the 0 plus box. So oftentimes you just have to bang it out. Remember, the 0 plus is corresponding to after the switch. So I'm going to draw after the switch. But the thing is, in this time, I have an unstable capacitor. So an unstable capacitor could be drawn as such. You can draw a capacitor. I actually have a tendency of drawing a source, but in this case, it's all good to just use a capacitor. Now, this would not be solvable if you did not know the 0 minus situation. Fortunately, you know the 0 minus situation, which means you know the voltage right here. That voltage is the voltage at 0 minus, which happened to be 0. If that is 0, if this is 0 volts, all right, this is basically a 0 volt element. A 0 volt element is nothing but a short. So this whole thing can be now drawn as such. Plus minus, put the 5 right here, and this is now shorted. Now, this is what we end up having, okay, where now I want to find this current right here. Well, if you remember, because this is a resistor in parallel with the short, this being nodes A and B, this resistor is effectively killed, okay? And this circuit is all that remains. The current is going to take this path right here, just like that. So if this is 10 volts and that's 5 amps, IC has to be, not 10 volts and 5 amps, 10 volts and 5 ohms, IC at infinity has to be 10 over 5 or 2 amps. And that would be our answer. So this is the solution to everything we needed in our first problem.